All right, we're going to do a 3D equilibrium problem that only involves forces. Here we've got the problem presented to us, and it has a crate being suspended that's supported by both two cables and the struts. And we're given all the dimensions for this. So basically the forces are being expressed to us in Cartesian format. Okay, and the weight of the crate is 400 pounds going straight down. Okay. The AD is in the plane Y and Z, okay? And C and B are in the plane X and Z as well, okay? So let's look at this now expressed as a free body diagram. So go ahead and pause the video and draw your free body diagram. All right, so this is the result of the free body diagram. All the forces are represented in red that we don't know. We do know this force here, which is 400 pounds in blue. I didn't write 400, should have. And I've dimensioned all of the locations here, so we know the change in direction and distance from A to D and C and B. Okay. So now that we're going to do that, we're going to take these and we're going to first determine the position vectors from A to B, A to C, and A to D. Okay, so basically look at A to B. Okay, so we're looking at how it goes from A to B, and we're going to be looking, and we'll notice that we move in the X direction, we move over 2 feet, so that'd be -2. And we're going to then go a distance of 6 in the negative direction on the Y, and then we're going to go a distance of 1.5. That's the difference between 4 and 1.5 up in the K direction, okay? So that would be my position vector. So go ahead and pause the video and write out all the position vectors for A to B, A to C, and A to D. All right, so this is the result of these position vectors, okay? Here, okay, these are all in feet. And also I have calculated the magnitude or the lengths of all these using Pythagorean's theorem. The next step is then to express the forces in Cartesian format. To do this, since we don't know the force AB, AC, and AD, we're gonna put in a placeholder of that unknown, and we're gonna multiply that force that we don't know, that magnitude of that force that we've been asked to find, by the unit vectors for these. And the unit vector is calculated by taking the position vector and divided by the magnitude. So go ahead and pause the video and then write all the forces in Cartesian format. All right, this is a result of these being expressed in Cartesian format, okay? And you'll notice that it's just simply the unknown force, FAB, times that unit vector, okay? So that's the position vector up top divided by the magnitude of it, all the way across, okay? IJK, and we did that for forces also AC, AD, and the weight. We don't want to forget the weight. Also note that I do put in the zeros, okay, as a placeholder. I want to keep that, and it's very important that we arrange these so that we have the I's in this direction, the J's, and the K's right above each other. Because what we're going to do next is we're going to use the equations of equilibrium. Summation of forces in X is equal to 0, summation of forces Y is equal to 0, and summation of forces Z is equal to 0. So we're going to sum all these up, okay? And the reason that I write it like this is all we have to do is transpose these and sum up now the columns. So this column represents X. So you're going to write up the summation of the forces in the X here, Y, and Z. Just make sure you multiply by the magnitude, okay? So go ahead and write the summation of forces equation. So you'll end up with 3, and you'll notice that we have three unknowns, and then 3 equations. The result of this is the summation of forces in X, and you can see here, don't forget to multiply by the unknown magnitude for each one. And you'll notice that how they're arranged is the forces AB is stacked right on top of each other in each one of these equations, and AC the same in AD. I've carried over the 400 on this side. It would have been negative on this side. I've put it on that side. And then we have now 3 equations and 3 unknowns. And I have another video in which I show you how to use on your TI-36 Pro. It's called the System Solve function on it. And I have that video, and it'll actually go through this. And this is a 3x3 linear system that you will use, and I'll show you how to do that. And the results from those calculations are here. Now you notice also I carry into all these expressions the fractions, which is more accurate. And here are the results. Now you'll notice that we have a negative 5.47. The reason we have the negative is that that's AD, that's a strut. We assumed that it was in tension, and since it's negative, that means we assumed wrong, okay, which is fine. So instead of this force going this direction, which we assumed, it's actually in compression, which we probably should have done, but I just wanted to show you that if you do get a negative number, that's what it means. So we'd flip that direction, and force AD is not in tension, but in compression, okay? So that's what that would mean when you see that. And of course, when we're just reporting the magnitude of the force in the member, it would be 547.